In this video, we're going to cover the questions from exercise 12.2 on page 139 of your physics book. We're going to look at questions involving speed, distance, time, angular velocity, and linear velocity. So as they go on, they get a bit more complicated, and as they get more complicated, they tend to get a bit more interesting. So we're going to start off with this question here. So a small object moving with constant speed in a circular path of radius 3 meters travels a distance of 40 meters in 2 minutes. Find its linear speed. So again, we've got to break this down and see what we're given and what we can deal with. We'll need to figure out what constants we're given, what formulas we can use, and what we're needed to find. So a small object moved with a constant speed in a circular path of radius 3 meters. So again, this will set this as a circular motion question, and we have the radius of 3 meters. So r equals 3 meters, which is a key thing. It travels a distance of 40 meters, so that's going to be s equals 40 in 2 minutes. So our time we'll need to convert from minutes into seconds. So find first off its linear speed. So as we're asked for linear speed, we can use the classic formula dad-silly triangle applied to the circle. So velocity is what we're looking for. The distance traveled, s, is 40 meters. Time is 2 minutes, which is 120 seconds. So velocity is distance traveled over time taken. So it's 40 meters over 120 seconds. So it's 0.3 recurring meters per second. So that's 1/3 of a meter every second. So 0.3333. Second question, we're asked for its angular velocity. So again, this is our first question dealing with finding angular velocity. So from our tables or textbook, we'll figure out that angular velocity is the angle traced out over the time taken. So we can look at that as omega is equal to theta over time. So the angle traced out over the time taken. Another way to look at angular velocity is that it is the velocity over the radius. So that's a second formula we can use. So omega is equal to v over r. So for this question, we know the velocity is 0.333 meters per second. The time is 120 seconds. We'd like to find theta, and we know the radius is 3 meters. So we look at these two questions, and we can use pretty much either formula for it. So we could use omega is equal to theta over time, except actually we don't know what theta is. In this 2 minutes, it could have gone around the circle multiple times or just once, so this wouldn't be a reliable formula to use. This second one here, the omega is equal to v over r, the velocity over the time taken, that's a more reliable formula to use, and that will give us our correct answer. So our velocity is 1/3 meters per second, our radius is 3 meters, so we get then 0.33333 divided by 3, which gives us 0.1 recurring radians per second. Next, we're asked how long does it take for the radius from the center of the circle to the small object to trace out an angle of, first off, pi over 2 radians, and then secondly 60 degrees. So how long does it take for the radius from the center of the circle to the small object to trace out the angle? So how long will it take to trace out this pi over 2 angle? So again, we're now in a new situation. We got a bit more information. Our angle is in the first part pi over 2. So we have our omega is equal to theta over time, which is our first formula up here. So the time then, if we manipulate this, we multiply both sides by t and then divide across by omega. So time is equal to theta over omega. We sub in our angle, we divide it by what we found our omega to be, which is 0.1. So we have pi over 2 divided by 0.1. So going to the calculator, that would tell me it would take 14.15 seconds to trace out this. And this angle, pi over 2, that will be 90 degrees. So it takes 14.15 seconds to go 90 degrees. Second off, they ask us for 60 degrees. So because we're dealing with circular motion, we'll convert 60 degrees into radians. So 60 degrees equals pi over 3. Again, you can convert this as before, or it's given in your tables. So the time is your angle, just like we have over here, angle over your angular velocity. So we have theta over 3 divided by 0.1 radians per second. And when we put that in, that gives us 9.43. And again, it's a smaller angle, so it should take us less time. So that's our first question in this section. So again, it's very formula heavy. You need to keep track of your information and use the correct formula. Moving on to the next ones. We then have a small object, I wrote that wrong, moving in a circle of radius 10 meters has a constant angular velocity of 4 radians per second. How long does it take to travel 1 kilometer? So again, we'll take our information as always and we'll standardize it. So our radius is 10 meters. Our angular velocity, which is omega, is 4 radians per second. And then our distance, which we're going to travel, our s equals 1 kilometer, and a kilometer is 1,000 meters. So we use the best formula. So here we have omega, we have radius, we have distance. We are asked to find how long does it take, so we're looking for time. So first off, we'll take this formula. We have omega and we have radius, so let's find the velocity. So again, we multiply both sides by r, so v is equal to r omega. We sub in our radius, we sub in our angular velocity, so we get 10 times 4 radians per second, so our velocity is 40 meters per second. Then, using Dad's silly triangle, time is equal to the distance traveled over the speed. So again, a bit confusing here with all the different letters, but it's the distance traveled over the speed. So from us, we'll be taking our distance traveled, our s, over our velocity, which is our v. So we have 1,000 meters traveled over 40 meters per second. So the time taken will be 25 seconds. Part 3. A wheel of radius 40 centimeters rotates with constant angular velocity. If a point on the rim of the wheel is traveling at 3 meters per second, find the angular velocity. So again, you might need to do a diagram just to figure this out. So you have a wheel of radius 40 centimeters. It rotates with constant angular velocity, so it's moving around at a steady speed. If a point on the rim of the wheel, so because it's on the rim, we know that it's on the outside. If it didn't tell us it was on the rim, then we wouldn't be able to find the velocity because it will be changing all the time. So we know it's on the rim, so we know it's 40 centimeters away from the center. So we then have radius is 40 centimeters, which is 0.4 of a meter. We've got to be consistent with our units. So it's traveling at 3 meters per second, which is a velocity. So we sub that in, and we're looking for the angular velocity. And again, when you have the right formula, it's pretty straightforward. Omega is equal to v over r. So our velocity is 3 meters per second. Consistent units over 0.40 meters. So it's moving at 7.5 radians every second. So then, question 4, a flywheel rotates with a constant angular velocity of 6 radians per second. Find the linear speed of a point at, first off its center, and then 30 centimeters from its center. A flywheel, again, it's not too fancy, it's just a wheel that spins around. So an exercise bike, for example, would have a flywheel in it. That's the bit that you're turning as you're pedaling. So first off, at its center, so again, we'll break this down as we have it before, the angular velocity of 6 radians per second, so that's our omega. We have the linear speed, that's what we're looking at, so we're trying to find this, and we know in the first question it's at its center. So if it's at its center, the radius is equal to the distance it travels, which is equal to 0 meters per second, because it's at its center, so it's only turning, it's not traveling any distance. So we use omega is equal to v over r, cross multiply, or multiply both sides by r. The velocity is r omega. The radius is 0 because it's at the center. The angular velocity is 6 radians per second, so the speed is 0 meters per second. So again, from our own logic, if you're standing at the center, you're not moving through space, you're just twisting. So you're traveling 0 meters, you have a radius of 0, so your overall speed will be 0. In the second question, you're further away, so you're 30 centimeters from its center. So again, we have to convert 30 centimeters into 0.3 meters. Again, we have our formula from here. The velocity is equal to r omega. R is our radius, which is 0.30 meters. We have our angular velocity, or 6 radians per second. Multiply those, and it gives us a velocity of 18 meters per second. So at the center, you have no speed. If you go out 30 centimeters, you're now up to 18 meters per second. As we move on, we're on to our page 3. So again, another flywheel question. So a flywheel revolves at a constant speed, constant rate of 40 RPMs. RPM is another unit for revolutions per minute, or rotations per minute, you could say, but it's 40 RPM. It goes around 400 times every minute, so revolutions per minute. Find the linear speed of a point on the wheel 2 meters from its center. So again, some of the information here is encrypted. We know we are looking for the we're given the constant speed, so we got to break down our information. So it's traveling at a constant speed of 400 RPM. So that means for our angle, and again that's the hidden thing, it's going around 400 times in a minute. So it turns 400 times in a minute. So 400 by 2 pi, because one full revolution, 360 degrees, that's 2 pi in radians. So the angle it traces out is 400 2 pi's every minute. So that's every minute. So when t equals 1, it goes around 400 by 2 pi radians. So our angle is 400 by 2 pi, that gives me 800 pi. So that's the angle it traces out. It's every minute, so that time is 60 seconds. So our angular velocity then, when we apply our formula, it's the angle traced out over the time taken, the first formula we looked at. So the angle traced out is 400 revolutions, 800 pi, so 800 pi over 60 seconds because it's a minute, and that gives me 13.3 recurring pi radians. Again, I just wrote as 13.3 pi. You could take your 13.3 recurring and multiply it by 3.14. So if you see a different answer, that's what happened there. So it says find the linear speed of a point on the wheel 2 meters from its center. So I've found its angular velocity, which is 13.3. Then we need to get the speed, the linear speed, 2 meters away from the center. Typically in physics, every full stop will have a question before and then a question afterwards. So we got a full stop here, so we got one thing to find, and then we got this thing afterwards to find as well. So we know the radius, we're trying to find the velocity. Velocity is equal to r omega, so velocity is equal to the radius by the angular velocity. We've just found the angular velocity. We've been told the radius is 2 meters, so it's just a case of multiplying one by the other. So the velocity is 2 meters by 13.3 recurring pi, which gives us an answer of 83.78 meters per second. So again, as long as you get the formulas and you can figure out the few bits of twists, like again, that's a bit different of RPM, revolutions per minute. There's a bit of decoding to be done there, but again, they follow the same kind of path. Now we're on to the sixth question. So it tells us the radius of the Earth at its equator is 6.4 by 10 to the 6 meters, and again, that's the true value. So find first off the angular velocity of the Earth about its polar axis. So again, complicated language. The polar axis is the line going from north to south. This here is the equator, so it's around the middle of the circle. So we need to find the angular velocity of the Earth about its polar axis. So again, we're expected to know certain things about the Earth and about our day. So one of those things we're expected to know is that the Earth spins on its axis once per day. So it goes around once every 24 hours. So again, we're dealing in physics, so we'll have to convert hours into seconds, but that's the first thing we're expected to know. If we're at the equator, you're going to go around one full rotation in 24 hours. And because we're at the center, again, every point of the Earth goes around once every 24 hours. But because we're at the equator, we know what the radius is. So the radius of this slot, this slice of the Earth, if you look in here, if you cut out the Earth and just have this disk, the radius is 6.4 by 10 to the 6 meters. So it's going to rotate around that once per day. So that would be a rotation 2 pi, a full circle, every 24 hours. So my angle is one full rotation, so it's 360 degrees, or we'll call it 2 pi for radians. In the time 24 hours, so 24 hours is 24 by 60 by 60, 24 by 60 to get minutes, by 60 again to get seconds, so it's 86,400 seconds. That's one full day. Then, once we've figured out that information, we're back to the same old formula. Our angular velocity omega is equal to our angle, which is 2 pi radians, over the time taken, which is 1 day, 86,400 seconds. So that tells us this really small figure here, 7.27 by 10 to the minus 5 radians per second. So in 1 second, the Earth only traces out a very small angle. Again, not surprising, because if you only go on a little bit, and if you join the lines up, that's going to be a very small angle. So the Earth only travels a really, really small angle every second, and it takes it a full day to go around 2 pi. So we're on now to our last part of this question, our last page of notes. It asks us then to, in a linked question, to find the linear speed of a small object at the equator. So if you were sitting on a chair at the equator, what speed would you be going? So for the quick answer, velocity is equal to r omega. We know both of these things before. The radius of the Earth is 6.4 by 10 to the 6 meters. We've just found the angular velocity, which is 7.27 by 10 to the minus 5 radians, which gives us a velocity of 465 meters per second. And that is a very, very large velocity. So even though you're only moving a small angle every second, because you're so far away from the center of the Earth, you're going at a very big speed. And again, that's just a quick way of doing it. However, if you're interested, we can take a look at where this comes from. So kind of from first principles. So if we work step by step, not building on what we had before. So as always, velocity is equal to distance over time. So that's our dead silly triangle. Velocity is equal to the distance traveled over the time taken. So the distance traveled is the circumference of the circle. So if we look at that slot of the Earth around the equator, the circumference is equal to 2 pi r. So then 2 pi is our angle because we're going the full rotation, and our distance is equal to r theta. So then that's a formula we've seen before. So our distance is r theta. We have our circumference, which for any circle is 2 pi r. Circumference is the distance around the outside. Full circle is 2 pi degrees. So our velocity is equal to our distance over time. So our distance traveled is over theta, that's over time. We also know that omega is equal to theta over t. That's our basic definition of omega. It's the angle traced out over the time taken. So we can take this theta over t and we can replace that with omega here. So again, that's how we get this formula. Velocity is equal to r omega. That is our derivation of that formula. And whichever way you do it, you should get the same answer. Finally, they switch this up. So while the first question dealt with the equator, this one asks us to find the linear speed of a small object at latitude 53 degrees north. So we got a bit more work to do here. So it's still going to be a circle, but it's further up, so it's going to be a smaller disk. This is like if we're looking down on the planet. So here will be the North Pole. This disk around here, this will be the path taken by the small object, and this one is at 53 degrees north. So as we move up in the planet, we're going to have a smaller radius. This green line here will be the equator. So that's our 6.4 by 10 to the 6. From the center of the Earth to the equator is 6.4 by 10 to the 6. But as you come north, up to 53 degrees north, you're going to have a smaller circle. If you kept coming up north to the North Pole, your circle will have a radius of 0 because you're at the top. Now, if we look, this is the side-on view. So you got your polar axis, your North Pole down to your South Pole. This line along here, this is your line going to the equator. We do a diagonal, and because it goes from the center to the edge, that is your radius. We're at 53 degrees north, so that's what that means, 53 degrees above the equator. So we got our equatorial line, we're 53 degrees north, and then this line here gives you the radius of your Earth. Here, this R53, that's the radius from the center of the Earth, from the polar axis. Yeah, the polar axis is better, the center of the Earth is down there. So from your polar axis to the place on the planet, that is your radius at 53 degrees north. So this little R down here, that's my radius at 53 degrees north. So it's important that you would do some diagrams to figure out what's going on here, because there's a lot of things that you could confuse. So again, I hope these diagrams help, but this is looking sideways, so that will be the equator. We go 53 degrees north, and then I think we're around about 53 degrees north, and then that will be the radius from the polar axis to the edge of the planet at 53 degrees north, and that will be the radius of this section here. So again, we have the radius of the Earth. We know what that is. It's 6.4 by 10 to the 6 meters. We have the angle 53 degrees, so we should be able to find this line here, this x, which is the distance from the center to this point here. That gives us a right angle triangle, so we can use our silly old Harry law. So silly old Harry caught a herring. So we have our adjacent, which is our x, and our hypotenuse, which is RE. So to find the radius up here, we first find x. So we're going to find the distance from here to here. So the cos of the angle is equal to the adjacent over the hypotenuse. Sub in our figures, the angle is 53 degrees. This radius of the Earth, the hypotenuse, is 6.4 by 10 to the 6. So we use our normal maths and we get that x is 3,851,616.15 meters. So that's what this is here. As we've made this a square or a rectangle, we have this length up here is going to equal to that length down there. So x was this figure, and x is equal to the radius at 53 degrees north. So we got this figure here. Now we come back over here and we want to find the velocity of an object along this path at 53 degrees north. So the velocity, as always, is equal to r omega. We've just found a radius, which is this figure here. We know our omega, that was what we found in part 1, so it's 7.27 by 10 to the minus 5 radians per second. So at this more northerly latitude, you're only traveling at 280 meters per second. So at this northerly latitude, because it's a smaller circle, you're traveling a good bit slower than you were at the equator, which was at 465. So again, there's a good bit going on there. There's a lot you need to calculate, and it's a tricky question. Diagrams are important, but we use our maths from before. We need to see what's going on, and then we have our new formula. The velocity is equal to r, the radius, by the angular velocity omega.